Welcome audience. Today's topic is understanding mass transfer phenomena and determination of relevant parameters. Mass transfer phenomena is a very important aspect in chemical engineering and in allied engineering applications, allied fields. Namely, there are many important mass transfer operations in chemical engineering is found, like a gas absorption, distillation, extraction, humidification and so on. Now, what is this mass transfer? Let us consider there is a mixture of gas having different species or liquid mixture having different species. If at one region of the system the concentration of a particular species is high compared to the nearby region, then due to concentration difference or concentration gradient, that particular species moves from the higher concentration zone to lower concentration zone. This is simply a mass transfer process. Mass transfer takes place in two different modes normally, one by diffusion, another by convection. An example of diffusive mass transfer, if we place one copper sulphate crystal bead in a stagnant liquid as shown in the figure, then copper sulphate molecules dissolves into the water and it diffuses away from the copper sulphate bead to the bulk water. The gradient of color, blue color, that shows how the molecules are being diffused, and as we go away from the copper sulphate bead, the concentration of copper sulphate molecules in water decreases, and hence the gradient shows, the blue color gradient shows how it is being diffused. Now, this diffusion is a process by which where we are not considering any movement of liquid. It is a slow process. For uniform concentration everywhere in the beaker, theoretically it takes infinite time. On the other hand, if we consider a plate that is given by the blue rectangle, it is coated with a red colored dye. Water is flowing over the system, the dye get dissolved into the water and water molecules and the dye molecules, they moves away with the stream of water. That is, in a higher concentration zone to lower concentration zone, dye molecules moves away by the bulk motion of water, bulk motion of the fluid. So, this is called mass transfer by convection. So, there are two different mode of mass transfer, one is diffusive mass transfer, another one is convective mass transfer. Now, in mass transfer, we think about the mass flux. Mass flux, say it is Na, it is equals to minus dAB del Ca del x. This is actually the Fick's first law of diffusion, diffusional mass transfer. dAB is the diffusivity of A in a mixture of A and B. Concentration is Ca and x being the direction of the mass transfer. Now, if in the liquid phase Na is equals to Kl, the mass transfer coefficient, multiplied by the difference in concentration. Here Ca is a higher concentration and Cab, let it be the bulk concentration. Now, at the gas liquid interface, gas molecule, it diffuses through the gas zone, comes at the interface of gas liquid and they goes into the liquid zone. In the gas phase, if we consider the flux as minus dAB del Ca del x, in the liquid phase, if we consider it is also proportional to KCl into Cai minus Cab. So, Na through Na we can equate this term and this term. If we want to calculate the mass flux, we can use Na is equal to minus dAB del Ca del x, this equation, or Na is equal to KCl into Cai minus Cab, this equation. Now, problem with the equation using this equation, that means Na is equal to minus dAB del Ca del x, that is we need to know the concentration distribution. In many situations, concentration distribution may not be obtained experimentally, or theoretical functionality of concentration distribution may not be available in some cases. So, we can go for the other part of the equation, that is Na is equal to KCl into Cai minus Cab. That means, if we can measure the two concentrations, one is the higher zone, higher concentration zone, other one is the lower concentration zone, we can calculate Na, and Kl is the mass transfer coefficient. Now, in the first part of the equation, dAB is the important parameter whose numerically to be evaluated. There are for gases dAB may be expressed as C into total pressure inverse into T to the power 3 by 2. So, this is the dependence of gas diffusivity with temperature and pressure. In the liquid phase mass diffusivity, this is may be correlated to Wilkie-Chang correlation. This is a well known correlation that is used in calculation very frequently. Now, this correlation contains lot of parameters, where dAB the diffusivity mu is the viscosity, T is absolute temperature, Mb is the molecular weight of the solvent, Va is the molar volume of solute at normal boiling point, phi b is the association parameter for solvent B. The values of phi b, some values are also provided here, like water it is 2.26, methanol it is 1.9, ethanol 1.5, ethane 1.0, heptane 1.0, benzene 1.0 and other non-associated solvents it is 1.0. So, these values are required to calculate DAB from Wilkie-Chang correlation. Now, molecular volumes at normal boiling point for different component which are required to calculate DAB is also tabulated here. We have got hydrogen, value of hydrogen, oxygen, nitrogen, air, carbon dioxide, sulfur dioxide, ammonia, water and chlorine. Many other values can be obtained from the handbook. Now, one important aspect is the interphase mass transfer and is their theoretical models. Now, when gas and liquid comes in contact, this is the interface. In gas, a component Ca that is dissolving into the liquid. Gas and liquid both are in turbulent motion as we assume. To calculate the mass flux, we need to calculate the mass transfer coefficient, that is KL. Now, over the years, almost 90 years of research on this, important theories or models have come out. There is a film theory 1924 by Lewis and Whitman, penetration theory by Higby 1935, surface renewal theory by P. V. Danckwerts 1951 and film penetration theory or film penetration model by Tour and Marcello 1958. These four are the celebrated theories or models has been put forward by the scientist so far. Now, in film theory, Lewis and Whitman, they assumes that on either side of the interface there is two stagnant film. Beyond the stagnant film in liquid phase as well as in the gas phase, the fluid is well mixed, having uniform concentration. These films offer the resistance to mass transfer in the gas phase as well as in the liquid phase. Experimentally, it has been found that the gas film is a bit thicker than the liquid film. So, the concentration drops across the film in liquid film as well as in the gas film. Now, concentration here in the gas film, that is at the interface, and concentration here, that is in the liquid phase, they are correlated by some relations. Normally, for the gas phase, partial pressure is used for concentration, and in the liquid phase directly concentration is used in the liquid phase. Now, due to the presence of this film, Lewis and Whitman they also assume that steady state mass transfer takes place across this film. These films are stagnant, and beyond the film the concentration is same everywhere due to intense turbulence. From their calculations, from their derivations, they found that mass transfer coefficient is equals to diffusivity by the thickness of the film. Now, this film has got very distinct advantage, this theory. The advantage is it is very simple to use. Mass transfer coefficient is proportional to first power of diffusivity, but it has got number of drawbacks. Number one, the thickness of the film is not measurable in most of the situation. Secondly, as the liquid is in turbulent motion, say in the gas absorber, both gas and liquid they are in the turbulent motion, the gas absorber. There problem is beingness of the stagnant film across the interface is questionable, because the eddies from the bulk, it comes to the interface and they again it is replaced by, or they moves away from the interface to the bulk again. During their stay at the interface, mass transfer takes place. So, the film is not, or film is not continuous, but it is changing with time. Its thickness may change, the film may break, newer eddies coming and going. So, their lifespan at the interface is very short, and within this short lifespan, steady state mass transfer occurs is too much of a simplicity. Also, the experimental finding shows that the power of diffusivity with the mass transfer coefficient, it is not 1, it is actually ranging from 1.3 to 0.667 or so. So, this theory is not matching with the experimental data. Maybe some data is supporting this theory, but most of the data falls out of the range, and the diffusivity, expression of diffusivity, it is somewhat else, but not 1. So, this theory was challenged by penetration theory put forward by Ralph Higby in 1935. He said that the eddies, it is coming to the interface, stays for some time and then it goes away. So, liquid film and gas film, they are in contact for a very small period of time, where unsteady state molecular diffusion takes place. And all eddies are coming because of the incipient turbulence outside the film or outside or in the bulk. The all eddies that are coming at the interface, they stays for the same time, their life age is for the same time. So, these are the assumptions in the Higby's film penetration model. The model equation and the initial boundary conditions for Higby's model is del C A del T is equal to d diffusivity into del 2 C A del x 2. With initial condition at t equal to 0, x everywhere, initial concentration is C A is equal to C A 0, this is the bulk concentration. Now, boundary condition 1, it is t greater than 0 at the interface, that is x equal to 0, C A is equal to C A I, interface concentration. And the second boundary condition t greater than 0, x tends to infinity, C A is equal to C A 0 again. Solving this equation with the set of initial and boundary condition, concentration distribution appears to be like this. It is a T increasing. So, theoretically, after t is equal to infinite time, t is equal to infinity, at different spaces, position and time, concentration changes and the family of lines, curves shows the changing of pattern of the concentration. The average mass transfer coefficient is expressed as K L bar is equal to 2 into root over d by pi T E, where d is the diffusivity and T is the average contact time. Now, here interestingly, Higby found average mass transfer coefficient is proportional to square root of diffusivity. Now, film penetration theory, Higby found that K L is proportional to square root of diffusivity. In contrary with the two film theory, where K L is proportional to diffusivity. Now, there are some drawbacks of this model, though it is much more realistic notionally compared to the film theory. There are some drawbacks. Now, what are the drawbacks? K L is proportional to d to square root of d. Experimental data shows a range of value the power of diffusivity like 0.67 to 1.3 to 1.7 for different cases, for different geometries, for different kind of flows, etc., in different kind of equipment. So, the fractional power of diffusivity experimentally not always 0.5. Now, though it notionally involved the turbulence effect, but only diffusional mass transfer has been considered in the model equation. In the surface renewal theory, Danckwerts in 1951, he actually modified the Higgs's model by assuming eddies that is coming at the interface will have a range of surface edges, range of lifetimes. So, he considered a surface edge distribution function, and which is given here, Danckwerts surface edge distribution function, and he obtained K L is equal to root over d s, where s is the rate of surface renewal and which is called the Danckwerts parameter. Here also, though the effect of turbulence has been thought up, but in the model equation, that is same as the model's equation considered by Higgs, it is same. Danckwerts also consider the same set of equation and initial and boundary conditions. The rate of surface renewal S is not measurable in most of the cases, or for very limited cases it is measurable. Now, in 1958, Tour and Marshall they put forward a reconciliation model between the film theory and the penetration type of theory with these boundary conditions to solve this differential equation. The only thing that is changed, there is a boundary condition 2 at t greater than 0, y is equal to L, C is equal to C A 0. They showed that for the large contact time, film model is good enough, and eddies that have small contact time, they follow penetration type of model, that is the Higgs type of model or Danckwerts type of model. At the same time, no model is acceptable until and unless it follows the experimental data, it is satisfied with experimental data. In many equipment under different flow regimes, many different geometries, to calculate the mass transfer coefficient, there is the most important parameter of this type of, when we use this type of models, mass transfer coefficient, a table of mass transfer coefficient and their correlations have been provided. Now, suggested reading for these subjects: Transport Phenomena by Bart Stewart Lightfoot, The Properties of Gas and Liquid, Reid, Pauling, and Fundamental of Momentum, Heat and Mass Transfer by Welty, Weeks and Wilson. These three are the celebrated books. It will help much in studying, understanding the mass transfer subject. Thank you very much.